we are in a conference room that's in some ways quite industry-focused, and this is because machine learning turns out to be good at a lot of things. In some ways, it feels like kind of all of a sudden after sort of many decades of work. And a lot of this success has arisen because of increasing sophistication in the models and the training procedures that we're using. Now, this is great. This is really fun, but it does mean that this area has become much less accessible to non-experts, right? That if you want to get going on a machine learning system, it feels like you need more and more training in order to get that thing to work in practice. So this is a problem as a methodological field, but also scientifically it's troubling because that means more and more details aren't going into the papers that you're reading at venues like NIPS and ICML. And so if you want to download you want to download a paper and reproduce its results and get the great result in ImageNet or whatever it is, this is something that gets to be sort of harder and harder. And there are a lot of examples of this in a lot of different sub-areas of machine learning, but here we are talking about deep learning, and deep learning in some ways is sort of the biggest culprit. And deep learning, it's great. Like I said, adaptive basis function regression, it's a good idea. And if you can tune these things very, very well, then you can get amazing results on a wide variety of problems for which there's a lot of data. And this has warranted big investments in building these kinds of systems for an increasingly broad set of domains. The problem is it often feels like you have to hire Jeff Hinton's grad student if you want to make this thing go, right? You've got to figure out all of these choices from number of layers, different architecture decisions, regularization, training rates, how big should my batches be. The list really goes on. And if you really know how to tune these knobs, then you can do amazing things. But if you don't, then it might not work and you might not know why. All right, so the question is, how do we sort of make progress on these kinds of problems, not just within deep learning, but more broadly? And the good news is that this is a kind of a task that we can systematize. Machine learning is ultimately about generalization. It's about getting good at making predictions about data you've never seen before. We have tools, things like cross-validation, for measuring this and treating this problem as something that's really sort of minimizing an objective function. The bad news is it's a very expensive objective function, and so we can investigate. We can kind of ask the question, how do people solve this in practice if you sort of out there in the world right now? And the unfortunate answer is something like black magic, right? This is an experience that maybe a lot of people in the room have had, where if you have a really small problem, maybe you could do something like grid search or something naive like random search and get reasonable results. But more generally, the kind of thing you're actually seeing is grad students sitting in a dark room twiddling knobs until they get their NIPS paper result, right? And that's not something that's really sustainable and isn't something that helps people who aren't the experts writing the code to tune it well. So these are just some examples. Force March is a more recent one we've heard about, where in some sort of industrial settings, people are sort of asked to get an improvement, say, on a speech recognition system every month, and if they don't, then there go their bonuses, and or perhaps their jobs. So we've got to be able to do better than this kind of thing, right? We have to be able to do better than either simple, naive heuristics, things that don't scale, and things that are not reproducible. And so the approach that we've been working on recently is something that's called Bayesian Optimization. And it's an optimization procedure, but unlike a lot of optimization procedures like stochastic gradient descent or linear programming or different kinds of situations where the objective function itself is viewed as something that's quite inexpensive, and perhaps you have things like gradients. Here, what we have is a situation where we don't have access to a gradient, and evaluating the objective function point-wise is something that's very expensive. And in that setting, we can afford to do some modeling to make very good decisions about where to evaluate this objective function. So just to be clear, this is an objective function whose sort of space, input space, is the set of hyperparameters, learning rates and things like that, in say, a big neural network architecture. And its output is something like, the thing you're trying to model is something like cross-validation performance, okay? And the idea with Bayesian optimization is that we can represent the uncertainty associated with what this true objective function is and make really clever decisions about where to evaluate it point-wise. And we can use, for example, Bayesian non-parametric models like Gaussian processes to do this and make relatively modest assumptions about what the space of functions are, and then also be able to manipulate things like the marginal likelihood and make predictions about good hyperparameters in closed form with just some simple linear algebra. But where the sort of really exciting part of this is the idea that we can, by using this proxy model for the objective function, we can deal with that, which is inexpensive, relative to an objective function that corresponds to training a bunch of neural networks that might take sort of weeks or months. And we can use the uncertainty to balance exploration of potentially new regimes where the model might work well against exploitation, which is kind of tuning up models in areas that you already think are quite good. So I'm not going to tell you about a lot of the technical details of things like Gaussian processes and stuff. There's a lot of great references, including like Kevin Murphy's excellent textbook. But let me give you kind of a cartoon that is that gives you kind of the intuition about this idea. So let's imagine that we just had a one-dimensional thing that we wanted to minimize, okay? And so there's like so the x-axis here is some parameter we care about. Now, in general, this works in multiple dimensions, but one dimension is easy to see. So this dashed line here is a function that's very, very expensive to evaluate. We want to minimize it, and we can evaluate it point-wise, okay? Here we've seen about 3 evaluations of this objective, and the question is, what should we do next, right? What should be the 4th evaluation of this expensive objective? And in a Bayesian setting, we can imagine lots of different functions that have support under our posterior distribution. That is, that they're consistent with the data and sort of live inside our prior. And there's lots of such functions, and we can imagine a really, really large number of these. And the question is, how do we make a decision that is going to be good in some sense under many, many, many of these hypotheses, okay, such that almost no matter what the true function is, we're making a reasonable decision and perhaps discovering something about what that function is. So it turns out that if we use things like Gaussian processes, we can actually reason about an infinite number of functions and actually think in terms of marginal predictive distributions of what the value of the function is at some new point in the space. And then we can ask questions about what we might expect to happen at some new location. In particular, since we're minimizing, we can ask the question, given this is my kind of current incumbent minimum here, represented by this blue line, we can ask the question, say, what's the probability that I'll do better than my current incumbent by evaluating at some new location? Or maybe in expectation, how much do I think I would improve by evaluating at some particular new location? And these are basically expectations that you can take under the tail of the distribution here. You can see these kind of contour lines, they're just kind of isocontours of predictions. We can imagine, okay, what's the probability that the functions are going to be dipping beneath our current best? And so we can form this proxy function that we can think about, in this case, something like expected improvement. What's the expected amount I'll improve over my current best? We can deal with this proxy function without having to go run our very, very expensive deep learning models and train them, okay? And we can maximize this blue curve sort of very cheaply. I mean, it's still a non-convex, annoying optimization, but it's something that's cheap. So we can choose the maximum of this sort of quality metric of a next evaluation, and then go off and run that, train that big deep network with those parameters. And then we get that observation, we perform a Bayesian posterior update of this non-parametric model, and then we reevaluate this acquisition function and iterate this. Okay, so the idea is we're gathering some information, trying to integrate out all possible functions that are sitting there and make a really smart decision about what to do next. And this is something we can iterate. And what's going to happen is we're going to perform a global minimization here. And it's going to zero in on this minimum. Okay? And the point is that it's not exploring regions of the space, for example, this region up here, where it's very, very, very unlikely to be a good global minimum. Okay, so this is kind of like a very nice idea. It's like just thinking carefully about how to do optimization of a very challenging objective when you have limited information. And like a lot of good ideas, it has a very long history. It's been invented in many different areas. It goes back sort of on the order of 100 years in statistics to things like optimal design of experiments, response surface methodology, and so on. Operations research folks think a lot about this as well. And it relates, of course, as well to a lot of important ideas in other areas of machine learning, so things like active learning. And there's some theoretical support for this approach as a global optimization procedure that I'm going to sort of skip over for now. So I'm just going to give you a little bit of an overview of some of these ideas and why this kind of works now when it didn't work, when it sort of hasn't worked for 50 years. And I think one of the main ideas is the idea of using sort of fully Bayesian optimization. In particular, one of the things that has I think, crippled these ideas in the past has been choosing point estimates for the parameters of the kernel that you're modeling these functions with. If you choose something too smooth, you can easily see how that would break. You would break such an optimization procedure. If you choose something sort of too bumpy, you can imagine that it would converge very slowly. If we choose point estimates in this very limited information setting, then we're going to wind up making potentially bad, sort of fragile decisions. In some other work that we've been doing over the last couple of years with collaborators, we've developed some very easy-to-apply Markov chain Monte Carlo techniques to integrate out these parameters of the Gaussian process and to make it straightforward to sort of account for that uncertainty. And this turns out to make a really big deal. And I'll kind of give you an idea of why that happens. So let's imagine that we're performing such a Bayesian optimization, and we have a couple of observations. Now, it's clear that in this very limited data setting, there are a lot of possible functions that could account for these data. But in addition to there being a lot of functions, there's also the possibility of many different length scales, many different kind of smoothness properties of these functions. There's some green lines here. There's a green line here that's very smooth, and then there's some other functions that are very, very bumpy. These would all cause us to make different decisions as we're performing this optimization. And the idea here is by using Markov chain Monte Carlo, we can actually integrate out this kind of uncertainty and make a decision that's going to be good under many different possible hypotheses. The issue is that, in general, I think for many years people have sort of resisted doing this because running something like MCMC inside your optimizer sounded like a crazy thing to do. But the fact is, if you're going to need a month of GPU time to train this neural network, then who cares if you run MCMC for 30 seconds? And that's kind of the underlying philosophy of Bayesian optimization, is that we can revisit some assumptions about optimization in the context of very expensive training procedures. Similarly, we can take advantage of this kind of probabilistic model to do parallelization. So the procedure the cartoon I showed you before was very sequential. I make a decision, and then I wait till it comes back, and then I run another one. But you can go on Amazon EC2 and fire up a whole cluster of computers to run a bunch of things in parallel. So we'd like to be able to make these kind of intelligent decisions, but in parallel. Fortunately, with a probabilistic model, we can fantasize possible futures. We can imagine, in a generative way, possible things that might happen from when we evaluate something. And we can try to make decisions that are going to be robust under all possible futures, and in a very similar kind of way. So to what we do with hyperparameters. So for example, let's imagine that we have 3 experiments that we've completed, and off in the cloud are 2 pending things. These are things we're trying, we're training, we don't know what's going to happen with them yet. And now we want to run a 6th thing. Some machine has come free and we can use it. How do we use it? And so what we can do is we can imagine possible futures, possible things that might happen when this guy comes back, and we can try to make it, and we can imagine that each one of those results, possible futures in a sense, would cause us to want to do something different with the 6th experiment. All right? And again, what we can do is integrate out these possible futures and make something that's going to be a good idea in expectation under many possible outcomes. And this allows us to get a very nice kind of asynchronous procedure for parallelizing these ideas. Okay, so that's just kind of a little bit of a taste of some of the things that allowed us to go from sort of Bayesian optimization as a nice but impractical idea to something that we can really use in practice and to make solve these kinds of problems. This has allowed us to do a lot of other kinds of modeling within this space. So, for example, sharing information across different tasks. Maybe you have several different visual object recognition problems you want to solve. You solve one today, and you're going to solve a different one tomorrow. You can use a vector-valued Gaussian process, for example, to share information across these and get very good on the second one or the third one after you've solved some intermediate problem. You can also share information across problem scales. Maybe you have a 1 billion image data set that you'd like to build a great neural network for, but it takes a month to train. You don't want to do that many times. You don't want to spend a lot of time exploring that space. You could coherently share information from small problems up to large problems under the observation that the successful parameters are going to be very similar. And we can, as I said, do this by sharing information across objective functions and making correlated predictions. This, in practice, gives us potentially quite a bit larger, pretty significant gains in performance. We've also been exploring other kinds of modeling ideas in this space. There's something we call Freezethaw Bayesian optimization, which takes advantage of the fact that often your training procedure, your objective function, is itself an objective function. You're training with something like stochastic gradient descent. We can model those training curves and then abort early different kinds of training procedures that look like they're not going to yield very good results. So you can wind up with kind of partially completed runs of training, again, like a big deep net, in which you don't have to finish in order to know it's going to be a bad idea and learn something about those hyperparameters. And this can give us, again, kind of very nice results. These procedures, in addition to sort of making it easy to automate these kinds of decisions, turn out to also be very good at setting these parameters. That is better than human experts on many problems, even the people who wrote the code. And over the last couple of years, at different times, and so these things evolve very quickly, we've had state-of-the-art on a variety of data sets for visual object recognition, speech recognition, automatic image captioning, and so on. So it's kind of very interesting and exciting because not only does it prevent you from having to, to tune this yourself, but it often can outperform the people who wrote the code. And this is something we've seen, is kind of picking up steam in a variety of different other areas as well. And like a lot of things, once we've discovered that we have a sort of an interesting hammer, you start to see lots and lots of nails even outside of machine learning, designing things like materials and turbine blades and compression algorithms and so on. This is kind of a particularly fun example of applying these ideas completely outside of deep learning. So there's some mechanical engineering researchers at MIT who study biomimetic robots, like this Cheetah. It's very hard to tune the control systems for these kinds of things. On the left, you're seeing somebody trying to, what is essentially weeks of work of trying to tune a control system for this biomimetic Cheetah. And on the right, you're seeing sort of literally overnight of Bayesian optimizing that same Cheetah control system. So this is all sort of fun, and we have research code that you can check out. But we've also been creating a startup to spin this technology out. And in particular to make it unbelievably easy to use, sort of on the order of 5 lines of Python code like this, where you define some parameters you care about, and you essentially ask what we call a scientist for a suggestion of what to try next. You go off and try that, and then report the result, and then loop. All right? So it gives you, with a very small amount of code, it gives you an idea of what you should be exploring. And you can, because of the asynchronous parallelism I mentioned before, you can have a bunch of these running on a cluster in parallel, and they'll all sort of play nice with each other and explore this parameter space. And then we have kind of a web interface that you can use you can check out, and a command line interface if you like to do things that way, to look at the data that you're gathering. All the computation itself is happening in the cloud. So I'll just wrap up there. So you can check out our sort of academic code, which we call Spearmint, for like you want to run a lot of experiments, and you can also check out our startup at whetlab.com. Thanks. I'll take some questions.